Assalamu alaikum and Bismillah Rahman Rahim. So today is the second lecture of week 12 and we continue with the topic that we discussed in the previous class, which was types of feedback in electronic circuits. So let's have a brief look at what we discussed uh, in the previous class. So this is the basic block diagram of a system with feedback, and this is the diagram that you are already familiar with. So X, Y and E can either be a voltage or current, as we discussed earlier. Furthermore, X, E and the output of the feedback block beta have to represent the same quantity, because we cannot add or subtract dissimilar quantities. For example, you cannot add a voltage to a current, neither you can subtract a current from a voltage. So if X is a voltage, E and the output of the feedback block have to be voltages. And similarly, if X is a current, then E and the output of the feedback block beta has to be a current. There is no such restriction on X and Y. For example, X can be a voltage and Y can be a current, or X can be a current and Y can be a voltage. Both X and Y can be voltages and both X and Y can be currents. So now let's proceed to the type of feedbacks that we have in electronic circuits. Before we have further discussion on the types of feedback, we also revise the reason why we sometimes like to have feedback in electronic circuits. And the reason was, as we discussed in the previous class, that when you have feedback and the product of the gain and the when the open loop gain is much larger than 1, that is when beta A is much larger than 1, then the gain with feedback or the closed loop gain is independent of the gain of the amplifier, which is represented by A here in this diagram. So in this case, when beta A is much larger than 1, the gain with the feedback, or what we can call the closed loop gain, is simply 1 over beta, where beta is the gain of the feedback path. Now the feedback path is, as we discussed earlier, is implemented normally using network of resistors. So the resistances are more or less independent of the frequency. So this means that when we have feedback, the gain will be independent of frequency in the uh, operating range of the amplifier. So we will get a flat uh, gain. Uh, and it is not just the frequency, but other parameters also affect the value of A, such as temperature or the supply voltage to the transistor in the amplifier. So uh, all these effects result in variation in A. So when we have feedback, variations in A does not affect the gain of the entire circuit, which is the closed loop gain A subscript F, and the closed loop gain is simply equal to 1 over beta, which is independent of A, which only depends on the resistances of the resistors used in the network. The only condition is that A should be large enough so that beta A is much greater than 1. And an additional point that we also mentioned in the previous lecture, that beta has to be smaller than 1 so that AF is greater than 1. So now types of feedback that we have is voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. So in the previous lecture we discussed voltage series feedback, so here we will just have revision of this type of feedback. So here A is V naught by Vi, beta is Vf or V naught. The feedback is in series with input. As we mentioned earlier, when you have series feedback, whether it's a voltage series feedback or it's a current series feedback, then the feedback and the input, they have to be voltages, because it's only in series that you can it's only voltages that are added in series. You cannot add currents in series. So when you have series feedback, then the output of the feedback block and the input both have to be voltages, and the closed loop gain is given by A divided by 1 plus beta A. We had the detailed derivation in the previous class of this equation. Now the next type is the voltage shunt feedback. So now voltage feedback means that the output is a voltage V naught, and shunt feedback, as the name suggests, the feedback is in shunt with the input. So now as the feedback is in shunt with the input, both the feedback and the input has to be current, because we can only add or subtract currents in shunt circuit. You cannot add voltages in a shunt circuit. So when you have a series circuit, the voltage across the series circuit is sum of the voltages, and when you have shunt circuit, then the current is equal to the sum of the currents in all the elements which are in shunt or parallel to each other. So when you have shunt feedback, the feedback and input has to be in shunt. Uh, Furthermore, the connection of the feedback block to the input side should be such that the feedback current is subtracted from the input current. And now we can see this point in this figure. If we look at node A, then the current entering node A is Is, or the source current, whereas there are two currents that leave node A. One is the II, the input into the amplifier block, and the second is If, the feedback current. And as we mentioned earlier, the feedback connection should be such that it is subtracted from Is. So now if you do nodal analysis on A, then the current entering node A is Is, whereas the current leaving the node A is sum of II and If. And this gives us the equation that is highlighted at the bottom of the slide. That is, II is equal to Is minus If. And this is what we require, that the feedback is subtracted from the source current. So the current going into the amplifier block A will be equal to Is minus If. So let's have a further discussion on voltage shunt feedback. Now A is equal to V naught by II, and beta is If by V naught. So A has the dimension of resistance or impedance. In case of voltage series feedback, A was dimensionless. It was simply the gain of the amplifier without any feedback. Here A has a dimension of impedance, whereas the feedback path has the dimension of conductance. This results in beta A being again dimensionless, as we mentioned earlier, because in the equation for gain you have 1 plus beta A, so beta A has to be dimensionless because 1 is a dimensionless quantity, so beta A has to be dimensionless. You can only add or subtract quantities of the same dimension. So we should always have beta A, the product beta A, dimensionless in this case, in the case of uh, feedback circuits. So now here we have the detailed derivation. So a starting equation is the II is equal to Is minus If, that is the current input into the amplifier block, that is the amplifier without feedback, is equal to the source current minus the feedback current. Then we substitute the expression for the feedback current into the first equation. So this gives us II equal to Is minus beta V naught. And then we can insert the equation for V naught, which is V naught is equal to A times II. So this gives us II equal to Is minus beta A into II, or II equal to Is divided by 1 plus beta A. So this equation is highlighted on the slide in yellow color. II is equal to Is divided by 1 plus beta A. And the next step is straightforward. V naught is simply equal to A times II, or which will be equal to A divided by 1 plus beta A into Is. So the gain with feedback, or the closed loop gain, is V naught over Is, and which is equal to A divided by 1 plus beta A. So we get the same equation that we have for the voltage series feedback, but with one difference. A has the dimension of impedance or resistance, whereas the denominator 1 plus beta A is dimensionless. So AF also has the dimension of impedance or resistance. This is also obvious from the very definition of AF, which is V naught over Is. So in this case AF is not dimensionless, it has the dimension of resistance, whereas in case of voltage series feedback AF was dimensionless. So this is another important point. AF and A will always have the same dimensions, as 1 plus beta A is dimensionless. So when you divide some quantity by a dimensionless quantity, the dimension remains unchanged. So AF and A will always have the same dimension. So the next type of the feedback is current series feedback. So as we said earlier, the first word of the type of feedback refers to the type of the output that we have in the amplifier with feedback. So current series feedback would mean that the output is in the form of current. So the output is certain I naught. That is the on the output side, the amplifier is acting like a current source, which means that the load will be in series with the feedback path. This makes it slightly trickier, so please pay close attention to the figure. So now you can see that starting from the passive terminal of the output of the amplifier, I naught goes into the load RL. So it can be anything with certain resistance RL, or we can even generalize it. So instead of RL we have ZL with certain impedance, and then after passing through RL, the current goes into the feedback path. So this is important. In previous cases where we have voltage as output, you can simply attach the load across the output terminals. So that's why we didn't even show it, because it's so simple and straightforward. You simply attach the load to the output terminals in case of voltage feedback. But the case of current feedback becomes slightly trickier. So you have to attach your load in series with the feedback path. So the current leaves the positive terminal, passes through the load, and then enters the uh, then enter the positive terminal of the feedback path, and then leave the negative terminal of the feedback path and enter the negative terminal of the amplifier. So this completes the output loop. Now coming to the input side, the input side is then straightforward. It's just like voltage series feedback, because we have series feedback, and as we said earlier, when you have series feedback, then the quantity that you have to choose is voltage, because it's the voltage that's uh, added up or subtracted in a series circuit. So on the output side, the we have voltages. Sorry, on the input side we have we have voltages. So the input is a voltage, and the output of the feedback block is a voltage, which is Vf, and the input into amplifier is also a voltage, which is Vi. So let's look further into current series feedback. So A, the gain of the amplifier without feedback, is I naught over Vi, and so it has the dimension of conductance or admittance. The gain of the feedback block is Vf or I naught, so it has the dimension of resistance or impedance. And beta A is again dimensionless, as we discussed earlier, because the equation for the closed loop gain, we have 1 over uh, sorry A over 1 plus beta A. So in denominator we have 1 plus beta A, and you can only add quantities which have the same dimension. So if you have 1 plus beta A, this means that beta A is also dimensionless, like 1. And here we have a look at the equivalent circuit on the input side. It's the same circuit that you saw in the case of voltage series feedback. So here you can see clearly that Vi is equal to Vs minus Vf. So the feedback voltage Vf is subtracted from Vs. So as we said earlier, you have to connect Vf with Vs and the amplifier block A in such a manner that Vf is subtracted from Vs. And here you can have the derivation for the gain of current series feedback circuit. So starting equation is Vi is equal to Vs minus Vf. Vf is equal to Vf is equal to beta times I naught. So we substitute this expression for Vf in the equation above. So we get Vi is equal to Vs minus beta times I naught. Then we insert the expression for I naught, which is I naught is equal to A times Vi. So this brings us to the equation Vi is equal to Vs minus beta A Vi, and at the end Vi is equal to Vs divided by 1 plus beta A. So the next step is straightforward, simply multiply by A and you get the equation for output. Before we conclude our discussion, another important point, the equation for Vi that you can see here, Vi is equal to Vs divided by 1 plus beta A, is same as what you have in case of voltage series feedback. So this is the equation for Vi, and then multiplying Vi with A, you get the equation for I naught. So I naught is equal to A divided by 1 plus beta A into Vs, and then gain is I naught over Vs is equal to A divided by 1 plus beta A. Now the dimension of gain with feedback is that of conductance or admittance, and this is the same as the dimension of A, as the denominator 1 plus beta A is dimensionless. Now the final feedback type that we have is current shunt feedback. So here the output is a current, just like the is the case for current series feedback. So here, looking at the output, you can see that I naught leaves the positive output terminal of the block A, enters the load resistance RL. So RL does not mean that it is just a resistor. It is simply the circuit connected to the output, and it's represented by its equivalent resistance RL. And if this circuit also contains reactive components, you can represent it by ZL. Then it enters the positive terminal of the feedback block, leaves the negative terminal of the feedback path, and finally enters the negative terminal of the amplifier block. So the output side is same as that of a current series feedback, but when we come to the input side, things are different, because here we have current shunt feedback, and shunt feedback means that the feedback path, the output of the feedback block is in shunt with the input, and when you want to add two quantities which are in shunt or subtract them, then they have to be currents, because you can only add or subtract currents in a shunt circuit. So the output of the feedback block is IF, and it's connected in such a manner that IF gets subtracted from IS. And here is an other important point regarding the current conventions. So going to the block A, that is the amplifier without feedback, for the output side it acts like a source. So the current leaves the positive terminal and enters the negative terminal. Whereas this block, the block A, which is the amplifier without feedback, acts like a load for the input side. So the current enters the positive terminal and leaves the negative terminal. Similarly, the feedback path acts like a load for the output side, because it takes the input, it takes the signal from the output side. So from the output side, the current enters the positive terminal of the feedback block and leaves the negative terminal of the feedback block. Whereas for the input side, the feedback block acts like a source, because it provides the feedback signal to the input side. So on the input side, the current leaves from the positive terminal of the feedback block and enters the negative terminal of the feedback block. just like you have in the case of sources. And the connection should be in such a manner that IF gets subtracted from IF. And the source and load convention, they are same for all the feedback blocks in uh, uh, in all the feedback types. In all the four feedback types, the block A, that is the amplifier without feedback, acts like source for the output and as load for the input, whereas the feedback block acts like load for the output and as source for the input side. So this point will help you remember the correct current convention for these two blocks. And the source of course acts like source, and load of course act like source, like load. So here A is I naught by II, so this is dimensionless. Beta is IF by I naught, so again dimensionless, and beta is dimensionless as usual. And finally the derivation for the gain of the current shunt feedback path. But before that, we have a closer look at the currents on the input side. So if we look at node A, the current entering node A is Is, whereas the total current leaving the node A is sum of If and I. So we have Is is equal to II plus If, and thus II is equal to Is minus If, which is the same case as we have for voltage shunt feedback. So the input side looks exactly like voltage shunt feedback, whereas the output side looks like current series feedback. So now we have the full derivation starting from the starting equation. II is equal to Is minus If, and If is equal to beta I naught. So we insert this equation and we get II is equal to Is minus beta I naught, and then we insert the equation for I naught. So we get II is equal to Is minus beta times II, or II is equal to Is divided by 1 plus beta I, and this is the same equation that you have for voltage shunt feedback. And the next step is straightforward, simply multiply II by A. So you get I naught is equal to A times II, which is equal to A divided by 1 plus beta A into Is. And now the closed loop gain, or the gain with feedback, is I naught by Is, which is equal to A divided by 1 plus beta A. So this is so in all the four cases the gain with feedback is A divided by 1 plus beta A, and the dimension of gain with feedback and gain without feedback, that is both AF and A, is that of dimensionless. So both A and AF are dimensionless. So let's summarize what we have discussed so far. So feedback in circuits improves stability, as we discussed earlier, as the gain is only dependent on beta, which is determined usually by a set of resistors. And in case of amplifier, the consequence is that we have flat gain or a wide range of frequency. And we have four types of feedback: voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. And the classification is based on this point: whether we have voltage series feedback or current series feedback depends on type of the output. If the output is voltage, we have voltage feedback. If the output is current, we have current feedback. And similarly, if and secondly, the feedback type basically shows the type of connection that we have and on the input side. So if we have shunt feedback, whether it's voltage shunt feedback or current shunt feedback, it means that the input side is in shunt with the feedback path and the input is therefore in form of current. Similarly, if we have series feedback, whether it's a voltage series feedback or current series feedback, it means that the feedback path is in series with the input, and thus the input and the output of the feedback block is a voltage. So this conclude our today's lecture. So what we have for next lecture? In next lecture we can have we will have practical feedback circuit examples, inshallah, and they include op-amp based circuits uh, and also FET and BJT circuits. So that's it for today's class. Good luck and Khuda Hafiz.